Hello everyone. I welcome you all for today's concept on digital signal processing. Today we'll be concentrating on module 5, that's digital signal processor. I am Mahadev, Assistant Professor, Department of ENC, Gaussian College of Engineering, Ramanathan. First, let us see the content. In the previous session, we already covered a concept of digital signal processor architecture. In today's class, we'll be covering an important concepts on digital signal processor hardware unit. First, let us see what are the hardware units present in the DSP. One is multiplier and accumulator. Second one is shifter. Third one is address generator. First, let us concentrate on multiplier and accumulator. So what is it, multiplier and accumulator? The DS processor uses the MAC, that is multiplier and accumulator, a special hardware unit for enhancing the speed of digital filtering. So when we want to use the concepts of filtering, we use this particular MAC for enhancing the speed of the processor there. So this is a dedicated hardware and the corresponding instructions is generally referred to as MAC operations. So whatever this dedicated hardware we have specific instruction sets for this particular MAC, and those instruction sets are called as MAC operations. Now let us see the basic structure of MAC is as shown in the figure there. Figure 1, the multiplier and accumulator. This is dedicated to a DS processor there. Okay, you can observe in this DS processor, there is a DSP processor. The multiplier has a pair of input register, each holding a 16-bit input to the multiplier. So the register X and the register Y has 16 bits, which is acting as an input to a multiplier. The result of a multiplication is accumulated in a 32-bit accumulator unit. So when we multiply two 16-bit numbers, we get the results of 32-bit, which is stored it in an accumulator. And from there, the result is stored in the result register. As the result register holds the double precision data from the accumulator. So this is the figure of the MAC operation, how it is performing the simple multiplier and accumulation operation. Okay. Now, let us see a concepts of shifter hardware. So in digital filtering, to prevent the overflow, a scaling operation is required. So some of the operations when we are performing, an overflow occurs. To avoid that, we use sometimes a scaling operation. A simple scaling down operation shifts the data to the right, while scaling up operation shifts the data to the left. This is a simple concept of multiplication and addition there. If we shift the data to the right, it performs the division operation, and if we shift to the left, it performs the multiplication. We can just analyze here. Shifting the data to the right is the same as dividing the data by 2 and truncating the fraction part. And shifting to the left is equivalent to multiplying the data by 2. Now let us see some examples. As an example 1, for 3-bit data words, we have considered here as 0, 1, 1, which is equal to 3 in decimal. When we shift 0, 1, 1 to the right, gives 0, 0, 1, because at the MSB we add 0 there. And this is equal to 1 in decimal. That is 3 divided by 2 is 1.5, and truncating 1.5 results in 1 because we consider the whole number there. Similarly, if you take another example of a 3-bit, I have considered even number 0, 1, 0. It's a 2 in decimal. When we shift 0, 1, 0 to the right, it gives 0, 0, 1, same as the previous one. That is 2 divided by 2 is 1. It's the whole number. There is no remainder in this. So here remainder is just truncated. In this even number, we got the whole number result there. So this is the advantages of shifting it right. So shifting right, we are performing a division operation. Now let us see by shifting it to the left. When we're shifting the 0, 1, 1 number to the left, we have 1, 1, 1, 0. That is 6 in decimal. That is 3 into 2 is 6. So which is nothing but multiplication. When we shift the data to the left side, we are getting the result as 6. So shifting left gives the multiplication operation there. So shifting 0, 1, 0, another example, number to the left, we have 100, which is nothing but 4 in decimal. That is nothing but 2 into 2 is equal to 4. So what here it performs is shifting operation enhanced the processor operation there. So shifting right gives us division operation, shifting left gives us multiplication operation there. So let us see the hardware unit which is been added in the DS processor. So the DS processor also shifts the data by several bits for each data operation. So what has happened is that to speed up such operation, a special hardware shift unit is being designed to accommodate the scaling operation as depicted in figure 2. Now you can observe that this is the DS processor, that is a digital signal processor based on the Harvard architecture here. In this Harvard architecture, you can observe that a special unit called a shift unit is being added. So due to the addition of this shift unit, the scaling operation, the performance is improving there and the speed of the operation gets increased. So in any advanced processor, a shift unit is being added to increase the speed of the operation. So that's the advantages of shifter. Now let us see the concept of address generator. This is another one important concept in the hardware design where a hardware block is required to point out to a particular address to perform certain operations. Okay, now let us see. Now already we are seeing the DS processor hardware unit. So this DS processor generates the address for each data, that is data on the data buffer to be processed. So whatever the data is being processed on the data buffer, an address bus is generated. A special hardware unit for circular buffering is used. Okay, a special hardware unit, a circular buffering is used. Okay, for generating the hardware. So you can observe that here we have an address generator block dedicated to the either data memory bus and the program memory bus. So figure 3 describes the basic mechanism of circular buffering for buffer having 8 data samples. Now we have considered a simple example consisting of 8 data samples and the data pointer is pointing to a certain address. Now here you can observe data pointer pointing to x of n. X of n is nothing but data. X of n minus 1, n minus 2, n minus 3, n minus 4, n minus 5, n minus 6, n minus 7. So we can assert that whatever the data is pointing, this is acting like an address. X of n minus 1 is the next address, n minus 2, n minus 3, n minus 4, n minus 5, n minus 6, and x of n minus 7. So this is one form of generating the circular buffer. There's the address generator. Okay. Similarly, we can take a simple example here. So in circular buffering, a pointer is used and always points to the new data samples as shown in figure 3. So whenever this data pointer is pointing, so we can easily analyze that it is pointing to the new data as shown in this particular figure there. After the next sample is obtained from the analog to digital converter, the data will be placed at the location x of n minus 7. So when the next data comes, it goes and stores at the location x of n minus 1. And the old sample is pushed out. So whatever the previous data is there, it gets pushed out of from that particular address location. Thus the location x of n minus 7 becomes the location for the current sample. So whichever the new data sample has entered the location, that acts like the current value. The original location of x of n becomes the location for x of n minus 1. So this x of n minus 1 shifts it to this location. So what happens? That becomes x of n minus 1. The process continues according to the mechanism what we described. This is a circular buffer formation. So for each new data samples, only one location on the circular buffer needs to be updated. So when you observe here in the circular buffer formation of address, only one data sample gets updated there. Okay. So this is one of the important concepts in the circular buffer. The same concept, how it is linked to a important memory location, we can take it example here called as FIFO, a circular buffer and equivalent FIFO. That is first in, first out. The circular buffer acts like first in, first out buffer, but each data on the buffer does not have to be moved out. So here it's not necessary to be moved out there. So what happens here? We can observe it in the figure 4. Figure 4 gives a simple illustration of 2-bit circular buffer. So in this figure, there is a data flow to the ADC, like A, B, C, D, E, F, G, and a circular buffer initially containing the address, that is the value A, B, C, D here. So the pointer specifies the current data of pointing to D, and the equivalent FIFO buffer is shown on the right. Now for this circular buffer, the equivalent FIFO structure is shown it here, and how the data is stored. The data is A, B, C, D, E, F, G. Now you can observe that this A, B, C, D is stored in the FIFO as in this figure, and the pointer is pointing to the current location as D. Okay. So now what happens here when you perform certain operations? So when E comes in, now after A, B, C, D, E is the data what we have. When E comes in, what happens? The data are shifted. So in the, as shown in the figure, in the middle one, the circular buffer will change the pointer to the next position. So if you observe here, circular buffer is changing the pointer to the next location here. Okay. So the circular buffer will change the pointer to the next position and update the old. So what is happening here is that the old data is getting updated with the new value. So it crosses the pointer only one moment to update one data at a time. So if you are using a circular buffer, what is happening? We are just changing only one data at a time. But what happens if it is in the FIFO? However, on the right side, if you observe, the FIFO has to move each data to let the new data to enter the top position. So what happens? When each data is moved, it takes 4 data moments in the FIFO cycle. Whereas in the circular buffer, it is updating only one data, that is A is getting updated here. Whereas in FIFO, what happens? Each data present in the address location gets updated. So in the last one, if you observe that, if another data enters in the bottom, drawing in figure 4, this is a figure 4 there, the incoming data F for both the circular buffer and the FIFO buffer continues to confirm our observation. If you observe the new data, what happens? The pointer is moving from E to the EF. So only one data is getting updated in the circular, whereas in the FIFO, all the data are getting updated. Like finite impulse response filtering, the data buffer size can reach several hundreds. Now, if you take an example of a practical application like FIR filter, we have hundreds of samples there. Hence, using the circular buffer will significantly enhance the processing speed. So in this kind of an operation, where the filtering is very, very important and only one data needs to be updated, this circular buffer address generation is very, very helpful. So in this fashion, the processor speed can be increased there. Okay. So when you compare to the FIFO, where all the data are getting updated, whereas in circular buffer, only one data has to be updated. That's the advantages of using the address generator. And one form what we are using is circular buffer address generator. Okay. So now let us see another manufacturers who are generating this particular digital signal processor. So DS processor has classified for general DSP and some special DSP there. What is that difference? The general DSP processor is designed and optimized for applications such as digital filtering, correlation, convolution, and FFT. So the general DS processor performs this simple operation of the DSP what we have, that is digital filtering, correlation, convolution, and FFT. In addition to these applications, a special DSP processor has the features that are optimized for unique applications such as audio processing, compression, echo cancellation, and adaptive filtering. Now, when you observe this special DSP, that is a digital signal processor, it is applying on the practical applications such as audio processing or audio compression or echo cancellation, adaptive filtering, or you can go even the video processing or a video compression or video signal transmission. So at that time, we go for a special digital signal processor. So here we'll focus on a general DS processor. In today's sessions and everything, we are just simply concentrating on a general DS processor. The major manufacturers in the DSP industries are Texas Instrumentation, Analog Devices, and Motorola. So these are some of the companies which are generating or manufacturing the digital signal processor in the today's industry world. The TI and analog device offer both fixed point DSP families and floating point DSP families, while Motorola offers fixed point DSP family. So here again, the industry is the way they are designing their processor, concentrating on two important parameters, that's on fixed point DSP and another one is floating point DSP. Okay, so we'll next concentrate on TI families and review their architecture and study the real-time implementation using the fixed point and floating point format. So in the next session, what we can concentrate is that we can take a simple example of a Texas industry family and we study some of the simple concepts of fixed point implementation and floating point implementation format. Okay. If you have any questions, go to the comment section, write down your questions. I'll answer to your questions. If you like this video, subscribe to my channel, click on the bell icon, or go to the subscription for further information there.